So in this example, it's worth just thinking a moment why this is not a principal value here. We've got 0 over 0 effectively at x equals 0. Just recall that sine x is equal to x minus x cubed over 3 factorial plus etc. So sine x over x, x minus sine x goes like x cubed plus x to the fifth and so on. So when we divide by x cubed, there's not a problem with the singularity. We've got a removable singularity at x equals 0. Okay, so how do we do this? Well, we always struggle with sine x, so we always try to convert to an exponential. So we realize, of course, that we can get x minus sine x as the imaginary part. Well, the sine x is easy. That's just the imaginary part of e to the, or minus sine x, e to the ix. To get the x, we just write ix. So x minus sine x is simply the imaginary part of ix minus e to the ix. So now, if I then write the integral as the imaginary part of ix minus e to the ix dx over x cubed, then I am in trouble at x equals 0, because at x equals 0, this is not x cubed anymore, because I've got basically at x equals 0, I've got this is 1. So it's not going to cancel. So I've got 1 over x cubed at x equals 0. So then I have a polar of order 3 at x equals 0, and I need the principal value. So this is a sort of contour that we're now, a type of integral we're now happy with evaluating using contour integration. So we have our usual contour, semicircular contour. Now we have a polar of order 3 at the origin. Other than that, there's no singularity. So basically we have this situation. Now by Jordan's lemma, we can argue that the integral around here vanishes as r goes to infinity. So we can write this is actually just the limit as r goes to infinity of this contour integral, or strictly the imaginary part of this. So yes, I'm skipping a few of the usual steps, but when you're along the real axis, this will just give you exactly this. The integral around the semicircle will vanish because of Jordan's lemma. So this then is just then the imaginary part of I pi times the residue at x equals 0. So it's the imaginary part of I pi times the residue of iz minus e to the iz over z cubed at z equals 0. So we need to work out this residue. Probably the simplest way is just by expanding the series. So we've got iz minus e to the iz over z cubed. Really what we're looking for is the z squared term. So we can actually save ourselves time if we only look for the z squared term, but I may as well just write it out anyway. So it's plus iz minus, plus iz squared over 2 factorial plus etc. over z cubed. So obviously the bit we're looking for is the coefficient of 1 over z, which will be minus times minus over 2 factorial. So it's just a half. So this residue here is just equal to a half, which means that the final answer to I is the imaginary part of I pi over 2, which is simply pi over 2.